Good morning, everybody. It looks to me like the signing in is slowing down a little, so we'll make just sort of a slow beginning. My name is Jason Ingham, and I am the chair or moderator for our online webinar today. For myself, I'm a professor of structural engineering at the University of Auckland and been connected to QuakeCoRE since the very early beginnings. Our speaker today is Enrique Del Rey Castillo. Enrique obtained his Master's of Engineering in Structural Engineering at the Polytechnic University of Madrid, which is his hometown in Spain. He then joined the Structural Analysis of Historical Constructions Master's program to learn more about advanced structural design, seismic actions, and the behavior of existing heritage buildings. This program was taught jointly at 2 universities in the Czech Republic and Portugal. Enrique's experience with the research project within the master's program motivated him to enroll at the University of Auckland to complete a PhD in seismic strengthening of concrete structures using fibre reinforced polymers. Enrique is now a senior lecturer and also associate dean in the Faculty of Engineering and Design at the University of Auckland, where he is dedicated to preparing the next generation of engineers, further enhancing the industry's knowledge and use of reinforced concrete and contributing as much as possible to reduce the environmental impact of the construction industry. Before we begin, just wanted to note that at the end of the hour, or at the end of the presentation, sorry, which is expected to go 20 to 25 minutes, I thought I would first take questions if they've been posted in chat. So anyone who wants to get in early or sort of like ask questions as they go, will just log them in the chat. And I'll clear those first and then any live questions as well. Until then, could I please just ask that people mute themselves? And again, if there's any questions along the way, just record them in the chat. And I'll give Enrique a bit of a brief warning when we've hit sort of the 20-minute mark. And other than that, Enrique, over to you.
Thank you, Jason. Perhaps the most important thing that Jason forgot to say is that he was my PhD supervisor. So I wouldn't be here without him.
That wasn't in the bio statement. I left that one out on purpose.
All right, so let me share my screen. I have to apologize because my voice is not that great. Actually, yesterday, last night, going to bed, I thought maybe I cannot even make it. But here I am. Can you all see my first screen, my first slide? Like that, no? Do you see the presentation version?
Coming through clearly.
Good. Thank you. I'll jump straight in then. So there is a big group of people behind me. I have highlighted my name not because I'm the most important person, but because I am the one that is here to take all the criticism. The most important people are the students. Without them, we wouldn't be able to do any work. So I have to acknowledge their very, very hard work, Mohammed, Tintin, and Junri. So this project started about 3.5 years ago when I won an MBA government funding to look at how we do seismic strengthening of diaphragms, concrete diaphragms with FRP, with carbon fiber reinforced polymers. I have to admit that a big part of the success of that grant application was because of the huge buyout from industry. So we have a big team of engineers, applicators, installers, suppliers, business owners, council representatives from New Zealand, from the US. They have similar issues in the US. So I think that's why it was so successful. Now, what is the problem? Diaphragms are key members in an earthquake. They distribute forces in between the different lateral system elements, walls or frames. And they basically tie the whole building together so it behaves like a building, is what is usually called a box behavior, rather than two walls that are 30 meters apart. Now, the problem is that back 30, 40, 50 years, this was not very well understood. The critical role of diaphragms was understood, but how to design them to fulfill that role was not that well understood. And the end result is we have weak connections along the diaphragm and between the diaphragm and the lateral elements. And one of the reasons why this building collapsed 10, 15 years ago is because of that. These things don't happen for one single reason, but the connection between the floor and the lateral element played a big part. Now, this is from 96, so it's 30 years old already. And this is how we understand diaphragms in New Zealand. In the US, they have a slightly different system, but in New Zealand, we think of diaphragms as strut and tie systems. It's basically a truss where we have members in compression that is taken by the concrete, and we have members in tension that is supposed to be taken by the steel. The problem is that the steel is not properly detailed, or the steel was a ductile mesh that cannot fulfill that role properly. Now, one of the ways to solve this problem is with carbon fibers, and it has been preferred over the last, 10, 15 years, because it's easier to install. Instead of bringing big, long, heavy chunks of steel, you are bringing rolls of FRP and cans of epoxy resin. So basically, you have something like that, where you are creating a grid line or an orthogonal grid of carbon fiber on top of the floor to fulfill those ties. This is not the same building, by the way. It's just an example. Another very critical role that sometimes engineers are asking the FRP to fulfill is as collector forces. They are collecting the forces in this particular case. Let me get the, I didn't mean to do that. Let me get the laser point here. In this particular case, we have walls in here, and this tie here, or this collector here, is collecting all of the gravity, seismic, inertial forces from all the way there back to the wall. And then it could be the same in the vertical direction, where we have that wall there, and we need to collect the forces from all the way here to the core. So we use FRP in this direction to collect the forces from there to that wall there. The problem is this is being designed, this is being used for many years, but in reality, we don't know how to design FRP for this application. We are using equations that were developed for other applications like 3-point bending or 4-point bending beams, or that were developed using sizes that are not realistic, often only like 300 millimeters long, 1 millimeter thick, and these ties are meters long and 3, 5, 7 millimeters thick. So it's not realistic. And that's where we started about 3.5 years ago. So we set up 3 big objectives with a number of sub-objectives. So the first one is to characterize the behavior of the FRP ties. We're not talking about diaphragms yet. It's just a FRP tie on concrete with no anchors, with different anchors. I will explain this in a second in more detail. Then we moved on to investigate hollow core units, precast units, and specifically the connection with the support beam. And then the global behavior, which is what we are doing at the moment, with in-plane flexural strengthening, shear strengthening, collectors, and then the overall diaphragm and building behavior. So starting with the first objective, we did a whole bunch of tests. I am not entirely sure how many, I think probably close to 200. And we leverage around 1,600 other data from public data and from our partners, Simpson Strong Tie. This is their lab in California. We did a whole bunch of tests there. We visited them, I think, 3 times. It's a very basic test setup. It's just a concrete block that we prevent from moving up with those steel plates or steel square sections, and we prevent them from moving out of plane with a roll in the back. And then we have the FRP here, and we pull from the FRP up. This is a schematic of the same thing. And then we have anchors in different configurations. You cannot see the FRP in there because we painted it. So we can use DIC, which is digital image correlation. And basically it's just tracking dots that we paint on the material during the test. So then a software can track those dots in the pictures and translate that to displacement, movements, and from there strains, which is what we have here. This is the block in the back. The FRP is between those two rows of black squares. We are pulling from the top up, and this is the strain gradient. So blue is 0, and as it approaches to yellow, approaches the rupture. So when I click next, hopefully the video will start. So we have a very stiff initial loading, and then the FRP is debonding, and the debond progresses down, the strain progresses down. This one has no anchors. So when the debond line moves from there all the way down, the debonding is progressing. Now, what this is telling us a few things. One is, even if this tie was 25 meters long, the load wouldn't go up. It will go longer. We will have more deformation capacity, but not more strength for capacity. And once the whole thing is debonded, it just goes. And now we have a piece of plastic on the floor, nothing else. It's not doing anything at all. So we did a whole bunch of tests, like I said before, I think 16 or 1800 in total collected from the literature and some that we did. And we realized that it's not about the strength of the concrete and it's not about the strength of the FRP. It's the ratio of the two that is determining the strain at which the FRP starts debonding. So just to give you a rough idea, I've put these 4 lines there. This is 1, 2, 3, and 4 layers of the typical product, the Sika that we all know, but they are all the same, Simpson or 5, they are all similar products in terms of strength and weight. So we can see that with 1 layer, we get about 0.4, but then it drops very rapidly. If we are using 4 layers, it drops to about 0.2% strain. With the rupture strain being 1% or 1.2 or 1.3%, that means the efficiency is about 20%. So we need to be very careful with this. We cannot use the rupture strain of the FRP for design. And then my student, Junri, put together this equation. So basically is linking the stiffness of the concrete, the stiffness of the FRP, and with a number, with a variable. The top one is for the average, the predictive equation, probable, and the bottom one is for design. Now you can see it's the exact same thing, just that name changes. Sorry, that number changes. And it changes quite a bit. It's like 25, 30% higher, right? So the spread is really big between design and average. And this is something that we are still working through, whether we use that equation for design or we use that one, and then we have a strength reduction factor or something similar to that. But this is just bond. This is the glue that is bonding the carbon fiber to the concrete, and that's the load path that we have, which is not ideal. We can have a higher demand than expected because it's an earthquake. We can have problems with construction, not the FRP or not only the FRP construction, but the building itself. We may have out of plane demands or deformations. We may have the bond in the compression cycles. So we cannot trust the bond alone. And if there are still people doing design without any type of anchors, just relying on the bond, and I think that is dangerous and irresponsible. So I would like to change that and start using some sort of anchorage system, almost always, pretty much always in a seismic environment. Now, I know FRP anchors very well because that's my PhD. I spent 4 years just thinking about this and working on this and dreaming about it. So I know FRP anchors very well, but I'm not the only one. There are hundreds of tests from other people. I propose this design method The paper was published 5 years ago, 6 years ago in 2019, and other researchers from around the world have tested it and it works. The only issue is that you need to use the average material properties, and they are not always shared by the suppliers. But this works, and it has been proven by many other universities. Now, this is the exact same thing. We are pulling from the top, but now we have an anchor here at the bottom. So the response is similar, elastic, then the debonding is happening, and now the anchor is engaged. So the anchor is giving us extra force, like over twice as much force, right? 35 to 75. But it's also giving us a lot of extra deformation capacity from 2 millimeters, that would be the inelastic, the start of the inelastic response, all the way to 12.5 or 13 millimeters. So the deformation capacity that the anchors are providing is huge. We still want to design to that level. Similar for steel, we are designing for the yield of the steel. We are not designing for the strength hardening, but we have that redundancy. So, once we understand this mechanism, it's not that different to the philosophy of design. It's not that different to steel reinforced concrete, normal steel reinforced concrete. We are using an elastic point, and we are counting on the deformation, inelastic deformation, for redundancy. It's the exact same thing. And this is not just one test. We have seen this repeated over many, many tests. This is 2 concrete strengths, 20 and 36 MPa, different anchor sizes. So the behavior is very repeatable. We have elastic, debonding, anchor. We can calculate those two. We can calculate the debond load with the equation that I showed before. We can calculate the peak load with the anchor rupture or anchor capacity equations, or the tie. If we design the anchor to be stronger than the tie, we can break the tie, not always. And then Junri, I should say, my student, is working through a model to calculate those deformation capacities. So we have this type of A, B, C, D, E response. The next thing we did is, well, sometimes the anchoring forces are huge and one anchor is not enough. So can we put 2 anchors together? Are they sharing the force, or are they going to break separately? So we put them 300 apart, 600 apart, like in that picture, and they share the load. So basically, if one anchor is 60 kilonewtons, both together are 120 kilonewtons, and that's the load we get, about 120 kilonewtons. When we put them farther apart, sorry that this is in inches because I work with the Americans, when we put them very far apart, this is the purple line, then we have one anchor breaking, and then the second anchor picks up the load and it breaks. So we could have a whole tie. Probably this is more similar to collector elements than to ties in a stud and tie system. We could have like a 30-meter long tie with anchors every meter or every 800 or every meter and a half. And we will get this zip effect where the anchors are breaking slowly one by one. This is also the end of Junri's thesis. So we are hoping to have a model where the engineer, the designer, can basically calculate these figures. So it could be A, B, C, D, E, or if we have several anchors, it would be A, B, C, D, E. But this is probably the end of that. We've done a whole lot of tests with shallow anchors because we have very thin topping slabs, sometimes 50, 75 millimeters. So we have tested that as well. We have tests on anchors installed in cracked concrete. So we can design for all of those different scenarios. The next one was the connection between the hollow core or the precast floor and the beam. And there were a lot of questions when we were framing up this research program about whether the FRP tie that is crossing that big crack, because the precast concrete cannot crack, right? It's designed to be basically without cracking. So all of the cracking is concentrated at that line. When the column is swaying sideways, the beam is going along for the right with the column. And we have a big opening in there. Sorry, give me a second. So there were a lot of questions about whether the FRP will survive that deformation demand, whether the capacity of the tie will go down because it's being pinched there. There is an angle there. So we designed a testing program based on previous tests, both here in Auckland and in Canterbury, part of the Recast project. And basically what we are doing here is we are building the beam, we are building the floor, and we are fixing the beam, and we are moving the floor up and down to simulate that moment opening there at the interface between the precast and the beam. And we have the FRP going along the way there. Then we have the actuator going up and down. We have done 7 tests with just rotation. And we are going to do, Mohammed is going to do 3 more tests where we have tension in there that is coming from the strut and tie mechanism itself, and then the rotation imposed from the 3-dimensional deformations of the building. So we are going to have both actions together. Now I'm going to go briefly over the 7 tests that we have already done. So we change the thickness from 1 layer all the way to 10 layers. And we saw a very predictable response. The debond strain was a little bit higher than what we would expecting. So from 34 to 38, from 35 to 42. But the response is very similar to the single tie test. We have a very stiff elastic response, then the debonding, and then the anchor picks up. Sorry about the volume. So this is at 6.5% drift, not strain. This is at the very limit of the test. We have a crack, but the FRP is fine. The anchors are there holding together the whole thing. I'm not going to show the rest, but basically this is extreme. It's 6.5% drift.
Enrique, this is your 5-minute warning.
Sorry?
5 minutes to go.
Oh, sorry. So by then, something else has broken for sure. Then we started to see issues when we went wide because we were breaking the beam. The anchors were not aligned in one line, so this row of anchors was taking the load before that one, and we damaged the beam. The FRP didn't debond, and this is what happened. We have a huge crack, and the whole beam is destroyed at 3.5% drift. So we decided to try different detailing mechanisms or options, and we were able to bring back the original response where the debond happens at around 0.2, 0.25. We have a minor crack and then debonds until 6% lateral drift. So this is working, and we know that we can make it work. Next step is to apply both rotation and tension. Then we are leveraging some tests that have been done by our partners overseas on flexural strengthening of slabs. So these are, from the top of my head, I think they are 4 meters long slabs that were strengthening flexure. So the chords, the flexural steel is not enough, and we are applying FRP, different Anchorage configuration, 42 tests. And basically, this is giving us an idea of how we can increase the moment capacity of that slab or of that diaphragm without compromising the ductile response. We don't want to increase the force, the moment, but then have a zero ductility, a very brittle response from the floor. That will not be very beneficial. Similar with shear strengthening, we have another 42 tests. The FRP is crossing the crack, so we have the cracks going on like that. We can see that in the test. The cracks go like that, and we have the FRP crossing those cracks. This is more challenging because it's shear failure. So we want to transform an inherently brittle failure to a more ductile failure. So it's proving to be more challenging. But some tests in Virginia Tech that I was involved with slightly have demonstrated that we can do this. We can increase the shear strength and we can shift the failure to another part. But it's very important that the FRP is anchored. For example, we tested, or they tested, I should say, FRP with no anchors, and the FRP just debonds and it does nothing. It's just a piece of plastic on the floor. And the whole slab just breaks down and starts to collapse. And this is the exact same test. It's anchored very well. The floor is perfectly fine. And we have transferred the failure to the shear friction connection between the floor and the wall. The wall is there at a much higher force capacity and with a more ductile failure. This is assuming that the starter bars are properly detailed, of course. If we wanted to strengthen that, it will be a different test. And I am done. A couple of minutes ahead, Jason. I hope that's all right. And I can take questions. You can also email me if there are more questions later on.